This video is produced by the UCD Math Support Centre in conjunction with the UCD Access Centre. In this video, we will be looking at how to deal with rational indices. In previous videos, which can be found online, we have seen how to handle indices from the set of natural numbers and from the set of integers. But what happens if we take indices from the set of rational numbers? So numbers of the form p over q, where p and q are elements of the integers and q is not equal to 0. So in the previous videos we saw that taking indices from the set of natural numbers could be thought of as repeated multiplication, and when we had negative powers, so indices from the set of integers, we could think of that as repeated division. The way we could think about indices from the rational numbers is as solutions to problems. So we'll look at that on the next slide. So let's look at solving x squared minus 2 is equal to 0. So the first step will be to add 2 to both sides. So x squared minus 2 plus 2 would give us x squared, and 0 plus 2 would give us 2. So we're left with x squared is equal to 2. To solve this now, we'll take the square root of both sides, and this will leave us with the solution that x is equal to either plus or minus the square root of 2. So in other words, we've found the numbers the square root of 2 and minus the square root of 2 that satisfy the original equation, i.e. if I sub root 2 or negative root 2 into the equation x squared minus 2 equals 0, it will be satisfied. So what is x equal to root 2? By definition, we have the following: that the square root of 2 is equal to 2 to the power of a half, and this is where our rational indice comes in. So we've seen that they crop up as solutions to equations, and often enough you can write rational indices as surd form, and surd form is the word for the square root of 2 or the cubed root of 2 and so on. So solving x to the n is equal to b, we'll look at a similar equation for x, so provided in this that b is greater than or equal to 0. So in the above we took the square root of both sides, but now we're going to take the nth root of both sides. So x to the n equal to b now becomes x is equal to the nth root of b. And the reason we took b greater than or equal to 0 is that if we didn't do that for certain values of n, we would end up in the complex world, which is not what we're looking at the moment. So just like above, we also have the definition that the nth root of b can be expressed as b to the power of 1 over n. Just like the square root of b, or the square root of 2, could be expressed as 2 to the 1 over 2. The cubed root of 2 could be expressed as 2 to the 1 over 3. In this case, the nth root of b can be expressed as b to the 1 over n. So in this way, just like we thought of positive exponents as repeated multiplication and negative as repeated division, we can see that rational exponents can often be thought of as solutions to equations. So let's look at an example of simplifying an expression with indices. So in this, x is a real number and it is greater than or equal to 0. So we will simplify the following: x is to the power of minus a half. So the first thing we notice is we have a negative exponent. So using the fact that x to the power of minus n is equal to 1 over x to the power of n, so when we have a negative exponent, this works for whether it's an integer or a rational number. It actually works for any number. So x to the power of minus a half becomes 1 over x to the power of a half. Lastly, we know that x to the power of a half is equal to the square root of x, and we saw that that's the two different ways that we can represent this in a previous slide. So the steps that we take to get to our final answer is that x to the power of minus a half can be expressed as 1 over x to the power of a half, where the index is now positive, and x to the power of a half is the square root of x. So we get our final answer of 1 over the square root of x.